بسم الله الرحمن الرحيم والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Hello everyone for attending this webinar which is about the installations and maintenance of solar photovoltaic PV systems. This webinar is organized by the Arab Union for Development and for Sustainable Development and Environment. And also it's organized by the Kuwait company called Sustainable Solutions for Consultancy and Training. We are glad to have this type of training which is part of our activities. This training is regarding to improve the skills dealing with the PV systems. We have our expert, Andreas Iliou, who's working in the field more than 20 years. He has highly skilled in the field regarding the energy auditing and the troubleshooting of PV systems. For this webinar, it's going to be about 3 hours. After the first hour finished, we will have like a break 5 minutes, and after then we will start our second hour. Before the third hour, we will have like 5 minutes break. After that, we'll have some times for the discussion. Regarding the discussion, you can use the tool of raise your hand icon, so you can introduce your questions at the end to our expert Iliou. Some guys will ask about the certificate and the slides presentations. You can contact the Sustainability Institute on the WhatsApp showing in the screen. This institute is certified by Public Authority of Applied Education and Training, and also it's registered by Kuwait Civil Service Bureau. For the recorded webinar, you can find it in my YouTube channel that's shown here, and also you can find it in the channel of Arab Union for Sustainable Development and Environment. For more information about upcoming events, you can check our Twitter and Instagram accounts. That's shown here, or you can message me on the WhatsApp, so I can share with you all the information. This is what we have at the beginning, and now we can leave the floor to Mr. Iliou to start his presentation. تفضل Iliou, it's your time.
Okay. So I take.
You can use the green icon. Yes.
Do you see it already?
Yes, I can see it here.
So no need to make a new. So everybody can see it, right?
Yeah, everyone can see it now, I think. Yeah. That's it here.
So let's start. I'm just checking now. Okay, good. So first to my, Salem already said some things about me. So I'm in LinkedIn also, so you can connect with me. I post a lot of installation videos and problems in the YouTube together also with Salem. Today we talk about installation maintenance and about troubleshooting an existing system. So when we troubleshoot the existing systems, we're looking at off-grid and on-grid system, and nowadays also on hybrid systems. So we need to know mostly the included materials, so the technical specification, the requirements, and the interconnection rules on each different country, as well the different setups according to the inverter manufacturers, which we can see that sometimes a German grid setting is used, or Italian, or in English, for countries who are new to PV systems. Mostly after 1-2 years time, then these settings will be fine-tuned to the settings from the country. So therefore we encounter sometimes problems in the beginning, but this can be fine-tuned, as said, during the fine-tuning of the different people involved. And so you have these best practices, and let's see when we dive into this. So for example, when you have a system set up and you do the commissioning, you should write down the phase, if they are balanced or not. This can be like in this example, for example, it's a little bit unbalanced already, so we are not feeding in, and we can see already 418, 422, and 419. So that's mostly the medium voltage side, which is already a little bit uneven. And of course, we are dealing with the transformers, which giving the phases 10 or 20 kilovolt. Here in this case, it looks like the middle one is a little bit up already, so it's not being used. There is a phenomenon in the industrial and in the household appliances that sometimes the board phases, that's also in America, there would be only 2 phases then, 120 and 242, and the neutral, and this is a European or EMEA with like 400 volt, before it was 380. So we can see that this one has already a problem with the unbalanced voltage, although we are not feeding in. This is samples which you encounter, like Kuwait, for example. That's from the previous years, so it could be maybe updated even. So we have 300 kV lines, underground overhead lines. We have several substations, and of course every country has got his own dealings with the substations, with the networks, with the if they go 33, or in Germany 36 kV, or 11 kV, or 22 or 20 kV. That depends on the different countries, and also the earthing is dependent on if an American or English substation was used, so the grid codes of America or US, France or England, or for example VDE, which also some countries in Europe and in Turkey and in some EMEA countries, they use already like VDE, or sometimes the British standard codes. That would be the sample for the grid in Kuwait. Of course, this is always different. That was for when I go to the sites and I install the systems, everybody else, they use PVSys, PVGIS. So there's different software-based scenarios, and you can see then payback periods. For me, that's not crucial, so I leave that out. So I don't mind what the system costs were at that time. So I'm more interested in the produced power, the capacity factor, the lifetime, and the energy shield. So when I go to the sites, I'm prepared or prepped with the possibilities of energy supplied and the energy yield, which theoretical should work like that. That was then split off into the monthly. So you can see in the different months the radiation, the incoming, the optimal angles, and then you can calculate the different scenarios. And also when you, for example, in UAE, Dubai or Abu Dhabi, most of the systems I inspected or I generally checked, they were very flat. So we're talking about 10 5 to 10 degrees on the roof, some with a 3 degree. So they're quite flat. So it's not in the perfect angle, but we will come to that later. So in this sample, for example, we have 52 degrees, 45, 30s, 15, and then the program will give you at the annual inspection the optimum angle for the whole year. That would be in this sample 26.8. That varies if you are in different areas, and then it gives you the theoretical orders. That would be now an app. So I have apps installed also in my telephone, which at the venue which I visited, when there would be an installed system, you would see the results very clearly, and that was then different scenarios, how many they installed. So there would be an installation in UK with the G83 protection. You can see on the left side the PV areas serially connected. Then you have mostly the DC isolator. Then you have the inverter, and then of course the AC isolator. And it's either multi-string inverters, central grid inverters, and all of these different supplied inverters have their pros and cons, of course. So when you go for a central grid inverter, he will not isolate certain areas, and if, for example, they're shaded, he will just overrule them. If the shading gets too much, the central grid inverter, of course, they will go off the perfect values and actually derate the other strings in a certain kind. So when you go to the sites during an installation, it's always best to leave the shaded areas off, or they only shade it in winter time, or maybe 1 hour or less in daytime. That's still okay. But if that goes over the border, so then many people install DC-DC optimizers, which is working. There's a Solar Edge, there's Tigo, there's Huawei, there's Enphase. So there's many manufacturers which gives you optimizers either as a standalone, so that's AC modules already. So you that's more for smaller system sizes. But I also encountered already megawatt installations with these type of optimizers. The good thing or the differences of optimized systems and normal inverter systems is that each individual, so it's either 2 modules or 1 module, they get configured on their own. That means each individual module get theoretically 100% output. That's different things like the temperatures, like soiling or shading, or not aligned to the sun, so either east, west, south, mixed systems. So each individual panel gives you more or less the optimum output, and the inverter will then combine the output in the Solar Edge system, for example. You will have like a 380 to 400 volt in America on the DC side. So that means when you have 10, 11 modules installed, that gives each individual module like 40 volt. So when you have the voltage of 50 or 45 volt on the module side, most of the newer modules are on this range, and let's say 10 amps, then these 10, 11 modules will give you each 40 volt and the optimum current, and then the inverter will just have these 380 to 400 volt as a source feeding into the grid. So the inverter on these specific systems is just synchronizing more or less. So he doesn't do the MPPT. He has got a fixed MPPT, while the other inverters, so like SMA, Fronius, many different suppliers, they of course go with the AC current. So for example, if you have a single phase or a three-phase unit, and you have a really high voltage at the site, like we saw just before, the energy of the MPPT has to be higher. So the voltage needs to be upgraded at the inverter side. So usually it's between 3 and 5 volt higher than the existing. And the more inverter you've got, the higher it gets. So you can measure up to 250, 255 I had in some installations. So it lifts actually the voltage of the individual house to a higher voltage. So each individual plug has then up to 250 volt, which causes also problems because the inverter will always feed to the maximum availability, and he will always search for the transformer, although more or less you use it on site. The bigger the system, of course, it will feed the transformer, but at the end of the day, it will stay at the facility. If it's an industrial complex or a mall or a high-rise building, then it will just go into the medium voltage side, and then of course go straight to the load circle. So it mostly stays at your house, and then of course you get the net metering. The problem, like I said, is if the voltage is quite high already at the transformer side, you can lower that. So we will have some slides later on where you can see that, and it gives you different fine-tuning possibilities. So that's the normal grid-connected system, you can say. So you have different voltages. Each individual panel gives you 30, like I said, 30, 40, 50 volt. And then according to the serial connections, mostly in the old times, it was 18 to 22 in a 1000 volt system. And now in the 1500 volt range, you have mostly already 30 to 34 modules sometimes connected in serial. So there is a blocking diode included, but those blocking diodes, they only work for each individual module. So here you can see the 3 steps. So for example, if you would install it vertical, which best you would not do, and it would be shaded, the fitted bypass diode will actually kill this module. So the inverter will lower the voltage, and then the bypass diode will kick in, and it will take one of these 30 volt modules, in this case 6 amps out. So it will make a shortcut, and then it will go to the next module, which hopefully is not shaded. In an optimizer scenario, it will create the 6 amps, like in this sample. So, and then, for example, if it's only, let's say this is a 180 volt module, 180 watt module, then it will shortcut 3 of these diodes in a normal inverter-based system. Now, if it's optimized, it will only cut off 1 or maybe 2 strings of these modules. So that means the 6 amps will flow, but maybe it's 20 volt or 40 volt or 60 volt. So you have 3 different cutouts on these bypass diodes. So a normal inverter will most probably cut out the whole module, while an optimized module can run with 6 amps and maybe 20 volt. So that means you have like 120 watt or 240 watt. So, or in a 180 watt module, in the old times, you would have then either 60 or 120 watt. So that's just in the old. Now we have 400 watt modules, of course, or 300 watt modules. It would be similar. So you have 3 stages. That means you have either 100 watt at full sunshine, 200 watt or 300 watt. And if one of the modules is shaded or cut open or has a soiling, then you will enter similar problems, and it will cut off most of the time one of these modules. And the more modules, of course, which are infiltrated with these shading effects, the less power you generate with the whole string. I have also some pictures where you can see the pylons. So like high voltage lines, people always expect if you have the high voltage lines and they are like 20, 30 meter above, and the lines hanging through, that they will not affect a system or very small. So they wonder then after a year that actually the plant is in underperformance cases sometimes 15 or 20 or even 30% off in these specific areas. And so it's not always the amount of shade, and also the amount of, if it's a small cutout like a lightning rod, it's worse. So a lightning rod, most of the time, if the wafer is not fully shaded, it will create a hotspot, and after a while it will get more and more, and then it will be, if it's not corrected quick enough, it will be a permanent damage. For example, Suntec and Hanwha and the different suppliers I worked with and worked for, they give normally a 30-degree variation. So that means if the wafer is 30° hotter in a whole module than the surrounding wafers, then you can replace it. In hot countries like Pakistan, India, UAE, Greece, Italy, so in Southern Europe, or in the desert appliances, that would mean you have modules with 70 to 90 degrees, normal wafers, and those hot spots would then go up to 120 degrees, 130 even, and that will then go into a thermal meltdown. So those modules will then lose warranty if it's wrongly built, or will be replaced if whatever applies. Here, if you, like I said, goes into a maintenance or installation, you have these string fuses. So you have to check the cabling, the string fuses. Normally it's 125. In some hotter regions, it's even 1.5. So of course, the higher you go, the more problems you encounter, because normally it's a factor 1. So if you have a 10 amp current rating of a module, and you use, for example, 12 amps, that's fine. If you use 15 amps, it's already a little bit high, and the possibility that it breaks down in a normal current is minimal. So what it does actually is there is a self-sufficient or self-maintaining mode in modules. So that came up with Sunny Mini Central at that time. That was like 2008, 2010. So we went through different scenarios. When I started with systems, for example, we had 50 watt modules and 80 watt modules. Now we have already 400 watt modules. So so when you had these modules installed and you had these different fuses, the self-maintaining mode was you could install 3 strings in an inverter, because most of the modules were then described as self-maintaining between 10 and 15 amps. Now it's some module manufacturer have already 20 amps. So that means 15 amps can continuously float into one string in a backfeed mode. Like I said, if it's shaded or soiled, or maybe some diodes are broken, a lightning strike hit. So that means if you have now 1, 2 modules less installed, mathematically added, because they are shaded or the diodes are not working, then you have these encountered problems, and then so from 3 installed strings in parallel without the string fuses, now you come up to 5 or 10 strings in parallel. So all of the strings which have on a higher voltage would feed into the lower voltage string. So that means 15 amps can easily be achieved, and then there would be permanent damage to these modules, and the string fuses will more or less blow. So that means it's this self-maintaining mode is condensed again, that you will have these security again, that once more than the amount 2 times. So like nowadays, in the old days it was 7-8 amps, so that's why we had the 15 amps. So nowadays it's almost 9-10 amps already, so we have already 20 amps. So if that happens, the shaded string or the problematic string during peak time and shaded, and the voltage of the MPPT will be higher than the affected string, then it will blow the fuse in a backfeed current mode. So while you install the systems, you go through some commissioning papers. One of these are, like I showed you, that would be the earthing and bonding scenario. So different countries, as I said, different local municipalities even have different installation measurements. So you go into that, and then you just check if, for example, you have to individually, like in America, France, and in the beginning in UK, you had individually bonded the earthing towards the modules. That's not necessary anymore. Suppliers and manufacturer went into that, and they give you now, for example, specific middle clamps or end clamps with a thorn inside, so they penetrate the anodized aluminum frame and actually earth the system then via the framing structure. Again, it has got an historical impact. For example, in Germany, it was not needed to earth the structure. So we had, of course, the transformer based, where you don't need it anyway. And then you have the rails, which you, after 2008, the transformerless inverter came up. Then just out of personnel maintenance and security and health and safety, they decided to earth the structure in case we have the 30 milliamps leakage rule, that there is a problem while you take off the module. You could get shocked. In UK, it's a touch and step voltage. So so indirectly, because it was transformerless, also in Germany, they used to earth the structure on a basis like a satellite dish or an antenna. Also, the structure was always earthed. It's also because of lightning strikes. What's interesting about equipotential bonding and protective bonding and different substandards in UK, when I commissioned the plants, they use thermal welding. So many people are used to that in Pakistan, India, UK, like I said, in some Arab countries as well. So they use copper plates, and then they bond them together around the substations. In Germany, it's more like a meshed approach. That's again coming back from these telecom laws in 1800, where all these telecommunications started. So that was an EMF criteria. So in Germany, they say the transformer more or less is the generator. In UK, America, they say the generator is the modules. Therefore, France as well, we have to earth the modules. So there's different sub ideas of earthing and why they do this. So still available or no?
Yes, Iliou.
Is it back? No. Okay. Okay, good. Okay. So that's according to the earthing. So like I said, in Germany they mostly use copper, sometimes even steel, and they use the concrete as the substructure. So most times the generator or the transformer is hooked up on concrete. Also some structures are on concrete, especially with the tracker systems. And yeah, so you have these different appliances, and once you go to the site, and especially when you're not only in your country, you have to check according to the local laws. Also, when you design a system or when you go to the site and do the checks, this, for example, is a graph I always use. If you change the directions like south facing, east facing, or west facing, you can see the more or less the differentiations. This is for fixed statistics in arrays. When you have now, for example, tracker-based system, then you're more or less always in the field of 93 to 99. So you have east-west facing structures on a tracker field, and then this one does not affect that. In hot climates also, if you have an east-west facing system, sometimes it's if it's fine-tuned and designed correctly, it can even outpace a south-facing system, because south-facing with a perfect angle will get very hot during midday. So even if it's in peak demand, in peak load and peak generation, you will actually get less energy because the modules, like I said, goes up to 70, 80, 90 degrees, and therefore will actually produce less. There will be some interesting graphs in UK. I did lots of commissioning and installing in the 2012 to 2018, and later on only commissioning and troubleshooting. You can see at the bottom, this is in line with Nice, France. So they have also 1150 to 1200 watt in Poole, Southampton, for example. That's the plant in Italy, in Sardinia. You can see the different variations: 417, 423, 419. So the inverter which are installed at the house on the right side, they have to feed now with 4 or 5 volt more, so to overcome the burden of the already existing. So one of the remedies here, for example, is first you try to balance the loads from the facilities. Then you balance your peak demand of your system installed, and then you lower the tap settings. So you can lower the most of the transformers have now 5 steps, some only 3. So you will check the tap settings of the transformer, and then you will actually go down to 400 volt. In some areas you can even go down, if it's a strong grid, to 380 volt. So 380 volt or 400 volt, you save 17 volt already at the inverter, because he will, like I said, upgrade the voltage to up to 5 volt. This is a system in Turkey, which is actually too low. So there I did the difference. I went up to 230 volt. So I upgraded the tap settings to 20 to 30. So that means there's a much stabler supply line. This was a 20 kV medium voltage, and like I said, the transformer or the module voltage inside the factory was actually supplying more power into the system to actually stabilize the malfunctioning transformer, so to say. So there was lots of extra power, so they had losses of 10% just because of the setting. Here in Cambodia, it's even worse. In some areas, and it goes even down to 190 when there's a lot of heavy loads supplied. So you need something like a line conditioner, or you use a hybrid system, or you use a hybrid system to actually use the batteries as a stable voltage. So you have 230 volts to begin with. That was in Turkey, it's a 33, that's another system, 2014. So you can see the different settings, 6 of them. So you can lower to 28.5 kV and up to 36 kV. So depends on you, what you find on site. If your system is on the low voltage side very high, like 400 volt, 420, then you pull it down to 400 volt, and you vary with the existing, with the tap settings. I think I have a picture. Yes, that's for example a tap settings. So you de-energize, of course. You go to the settings. You put it from 1 to 5. So that's normally they get delivered with setting number 3. Here you put it either to number 2 or to number 4. And then you will find out a different scenario. Either the voltage will increase or decrease, depending what problems you encounter on the site. Also, check the earth of the transformer, and if there is an earth connection towards the inverter, if it's a big system. Otherwise, you could even get increased transmission line losses due to transients and either the under voltage or the over voltage, as explained. That's some systems in Vietnam. You can see some hybrid systems. With different scenarios when they feed the batteries or into the grid. So that's a 3.9 kilowatt system, and you see the discharging of different scenarios. That's the production. Like I said, this is a small system, but yeah, it will take over the loads. Most of the systems are 48 volt, so from 48 to 60 volt, depending on the batteries you use. There's also some with 50.2 volt already, so they charge with a different cycle. Most comes with apps. You can see here another supply in another area. There it's 221. That could be next to the transformer. And then you have only 9 volt differences to 230. But anyway, these line conditioners or these hybrid inverters will stabilize the grid for you. That's the backfeed current explained in the beginning. So, like I said, of course, there are, at that case, 17 modules installed, but just to see the flow of the different backfeed, the 17 modules try now to backfeed the 16, 15 modules, depending on how much voltage the inverter is generating. So if it for example, hits the 16 modules, then both of these strings will feed the 15 modules. So if the 15 modules, like I said, are shaded, soiled, or have some other anomalies like lightning strike and diodes failures, so they will shortcut all the time, then those voltages, mostly in the beginning and in the nighttime when they reach 600-700 volt, then these two strings will get the backfeed current. So that's also all these mismatch losses. So it could work during daytime, when the sun hits 5 hours, 6 hours, because then the voltage is getting usually with the old system for 500 volt. With a 1000 volt system, it's mostly 600 to 700 volt. So depending on how many diodes are defect or how many modules are soiled or temporarily out of operation or optimal operation, they will get hurt all the time. So that could happen daily or monthly or weekly, but it's a problem. So that's, for example, another app which you can see with different tilt angles, with the money more or less earned, and you can show these. This one is, for example, a little bit out of south, but it gives the money back. So once you go there and you have an idea what the system can make on this roof, if it's a south facing, or how much power you actually can achieve, and then of course the different tilt angles. So you can see January, December is more or less the same, November and February is the same. Then you have these October, September, where it's 16 and 20 and 10 degrees optimum angle, and then you have the other ones which is on 0. So there you can see most of the time these systems have 5-10 degrees installed, so they work best in summertime and a little bit less in winter. So again, if you angle them on 10 degrees, it's also a little bit better for the rain, if there is rain, and also the possibility of cleaning is a little bit better. And if you not angle it perfectly to the sun, the modules also tend to not overheat so much. So if you, for example, use the 10 degrees, it's a little bit off. That means the temperature is mostly 10 to 15 degrees lower than in optimal place, because in perfect timing and in summer, they will dramatically heat up those modules. That's a power grid in Germany. You can see the huge amount of transformers, substations in Germany used. So that's why sometimes when you, for example, also study in Germany and they give you these different programs, PVGIS or PVSys, and you go then to other countries and try to copy those installation. I mean, European climate, first of all, especially in Germany, is very cloudy. So there's like a 1,000 to 1,200 kilowatt hours per kilowatt peak installed. So a 10 kilowatt system can give you between 10 and 12,000 kilowatt hours a year if it's only feed in. Now more popular are these hybrid systems where you actually charge batteries and use it also for self-consumption. But you should know roughly what a system like that can give you on the long run. So in Abu Dhabi, 1,700 to 2,000 even are possible. But then we have haze, and then we have sand-based soiling, so it has to be cleaned. So there are variations. I mean, there's also some pictures coming. I was in Benban for one supplier. I did some commissioning there. So they upgraded, as you can see, transmission lines and the substation for this system quite a lot. What you have also in America now, and also in Australia, a lot of wildfires and some power outages. There's also upgraded workflows on this. Now, for example, Tesla batteries, storage system suppliers, they have wildfire and also during hurricane season. some charging capabilities that they actually charge with the grid, if it's allowed, and with the solar system up to 100%, because they know something could happen, for the possibility of a, if you think about a hybrid system, that actually the grid will either be on purpose in a rolling blackout scenario, or also in South Africa right now, or in other countries. So they try to give you 100% of battery startup, and then of course if you use that and you have a solar battery backup installed, then they will during daytime of course charge your batteries further on, or you use during daytime the whole battery bank. What you do have in the old systems, I saw, this is an inspection, the island phenomena. So what happened is, during most of the underperformance issue I encounter, is that the system goes island, or shows it goes island, or for example, the AC has an undervoltage, a tripping point, low voltage, frequency hopping. This is sometimes caused actually from an ISO failure. So you have these phantom ISO faults, I call them. So if the system is not perfectly aligned, which we will see later on, into the earthing structure of specific transformer and inverter settings, then you will also have problematic issues which show up at the inverter, but in actual fact is a completely different problem. Here, for example, that was a 300 kilowatt system per farm stall. They had always trips between 11 and 12 and 12 and 1 o'clock. So what happened was actually one of the phases of these inverters caused an interruption and some transients, and it caused the phase to vibrate more or less. So the other inverters picked that up and switched off. So during this cascading effect, more and more inverters switched off, because the next inverter made the same measurements. And then you could see something like a frequency or a problem with the LT, which is the CT, or you had a problem with a stationary problem of the LT or CT or VT. So all these frequency problems at the memory could not help me. So I checked different supplies. You can see here, for example, that was one of the worst days. So this guy lost 4 to 5 hours, constant problematic issues. So also the transformer was on 220. So I changed the taps to 230, and then I had to upgrade the earthing, and then they used also a TNC system. I will come to that later. What's the problem with that? That's what I expected. Like I told you, some systems, 2011, 2010 in UAE already, there were 600 to 1 megawatt with a green roof underneath, quite flat. So they had sometimes problems with the cleaning, because the soiling is quite severe some period of days. Yes.
Sorry, you can move on.
Okay. So In this system, for example, that was the old trios with the RBB. You can see they were still installing the system. There's some old structures there on the left and right side. So there was the problem also from these phantom isofolds, and the modules were old technology, good and proven over and over again. But in this system, it failed. What happened was, I don't know if you can see that, but the old lights on the right-hand side, you can see two lights, and in the middle there's also two lights. So they used an earthing strip on top of the garage complex where we have the cars, parking garage. But it was not combined to the AC inverter, and it was not combined to the transformer station. It was a lightning projection straight down to the soil. So the inverter did not pick up those earthing rings, so he could not see the plus and minus. So whenever they cleaned the modules, whenever it was raining, and whenever in the morning during dew, so if it's very hot in the desert, and then in the nighttime it gets a little bit colder in some times of the years, then they picked up these phantom isofolds. Phantom because it is not a real isofold. There was no, most people try now to change the cabling, pinpoint inverters, which you can't. So a phantom isofold also, I must say, is very difficult to find, but it's a rolling inverter problem. So it's not always the same inverter. If it would be always the same inverter, it's very easy because you fix the cabling of the one inverter, or maybe you take some modules out or some strings, and then you can see if maybe the connectors are at fault or some substrings. But as I said, a phantom isofold is something different. There is no equipotential grounding in between the facility, so the house. It's worse with a concrete roof, with a corrugated roofs or with roof sheets, because you have a capacitor. Here it's a concrete roof with a parking deck earth, and like I said, went straight to the ground, but no interconnection. So here in this example, it was enough just to make two earthing connections towards the inverter, and then you had the same input as the output. Here you can see the soiling effect after haze or sandstorm. And also what's interesting is when you see the parapet walls on the left-hand side, so the modules more to the side of the roof, they have this stuck effect. So they were 55 degrees, soiled, of course, like I said, and the one nearer to the open space where there's like a self-creating breeze are at 50 degrees. Once they were cleaned up, which you see on in the front, they went down to the normal NOCT values. So the best, if you see a problematic roof, is to, of course, check the modules as they are, check the underperformance, clean them, and see if, first of all, if the temperature goes down, second, if the current goes up, and if the output of the system goes up as well. Sometimes the AC inverters are derating. Sometimes the DC, as you see, of course, are derating the output. So you have to give him the chance to do his work. And in areas where it is like colder and hot, like in Europe, especially, you have a lot of good working systems with like 18 modules or 16. And in summertime, all of a sudden the system derates or degrade the output. It's most of the time not the problem of the modules or the inverter, but it's a combination. So some inverters, especially during 2010, 2015, they had quite a narrow window of the MPPT. And if you did not give him enough MPPT, so you must imagine in summertime, those modules per panel, they're losing roughly between 3 and 5 volt. So depending on the angle and depending on the heat and depending on the influx of energy, one module loses the worst 5 volt. That means a string of 18 or let's say 20 modules lose already 100 volt. So these 100 volts you will never get back to the inverter. Hence, they try, or they will suffer the consequences during hot periods of time. So in winter time, you win a little bit, like 0.5 to 1 volt maybe, and also the current goes up. So the cooler the modules, the better the output. So a lot of systems in winter time installed because of the different feed-in scenarios and winter goals that to December or to January they have to be finished. The system were working till March, April, and then after 3-4 months, the system were not working. That is because, like I said, you have to check the MPPT. The MPPT of the modules and the MPPT of the inverter has to be matched somehow. So if the inverter or the modules, that's where you go into with an IV measurement, you go into with a C-word or with a banning or whatever device you've got, even a voltmeter, you can see the string voltage. And if you have a banning, C-word or HT, one of those devices, you measure your strings, and then you can see that the voltage of the modules are already derating. That means they are below 600 or below 500, but the inverter is expecting between 6 and 580 mostly. Then he can further go down, and then you can see the modules added on these serial strings are not enough. So they work in winter time because they're cold and there's output, but in summertime when they lose an additional 100 volt or 80 or 50, depending on your system, you have to always think back, who installed the system, who maintained the system, and are the connectors good? You have also devices like Emasys, where you can check the connection of the cables. You can check isolation faults. You can check which modules are actually has the problem. So there's a lot of additional thermography and different setups. So if, for example, the owner of the system tells you they already did clean the modules and there was no improvement at all, or the improvement was 5% maybe or 10%, but only for a week and then it was away again, that are those issues. So the issues are mostly two less modules. Would you install it? I'm always going to the roof. Of course, 10, 20 years ago, or 30 years even, I installed systems completely different. There was different inverters, different modules, and you grow up. You can see the momentum. The modules get better. Sometimes the inverters are better. Sometimes the combination of some inverters with some modules just don't work. That's a fact. So some inverters or some modules are too high in current. So they only can do like 15 amps. That's the old version of the modules. Now you have inverters or modules with 10 amps per string. So you cannot double up the 10 amps per string because now you're exceeding the strings because it can only take 15 amps. So you have to think 5 years back, 5 years up front, and with every different technology, as we saw when we went from 600 volt to 1000 volt, or from 1000 volt to 1500 volt now, it's evolving and it's changing, and also the modules change. We had from the hype 600 volt to 1000 volt, all of a sudden we had PID, which we did not have so much with the 600 volt technology. We did not have it at all with the transformer based. And then you get the PID boxes, you get harmonic filters, something gets added, something gets subtracted from the inverters. So you have different problematic issues. Now we are at this effect of the oversizing. So the oversizing of the PV is, like I said to you, similar to the fuse. It's 127 to 1.5. So some desert areas, especially in America, most of these areas, they use already 1.5. So like a 15 kilowatt system with a 10 kilowatt inverter, or 150 kilowatt roof with 100 to 120 kilowatt inverters, DC to AC, because it's known that they derate a little bit during summertime. And then if they derate, you can see the cap on top of the system. So when the power limitation kicks in, you can see a flat roof. And best is when these flat roofs occur, it's maybe 10 or 20 days max in a year's time. That's still okay. If it's more, we have to think about something. Do you want to make a break?
Mr. Yeah, I think if you like, we can have a break now, 5 minutes. You can relax 5 minutes and we can start over again. Okay. Dear guys, now we will have like 5 minutes of break and then we'll start again after the 5 minutes. Now we have in my time, it's 7:13. So we will start at 7:18. Thank you and stay with us.